Now we will discuss the synthesis of cortistatin A. The first synthesis of cortistatin A ever was in 2008 from prednisone by Dr. Kobayashi at Harvard University. In 2010, three researchers at Harvard University built upon his work, named Alec N. Flyer, Chong C., and Andrew G. Myers. They synthesized multiple cortistatins, A, J, K, and L, but we will focus only on cortistatin A, the most potent angiogenesis inhibitor. They began their synthesis using an alpha-methylene ketone, seen here. Over 11 different steps were used to synthesize an intermediate called azeto-alcohol 5, seen here. This azeto-alcohol 5 is an intermediate for several cortistatins. This intermediate was used to synthesize cortistatin A precursor, which eventually was used to synthesize cortistatin A. We will now elaborate on the techniques used by the researchers to complete their synthesis.
Now we will discuss the synthesis of the intermediate azeto-alcohol 5. A known alpha-methylene ketone 15, seen here, was selected as the starting material for the synthesis of the azeto-alcohol 5. Phosphoionosilylation of alpha-methylene ketone 15 with triphenyl phosphine and triethylsilyl trifluoromethane sulfonate at 240 degrees Celsius in chloroform creates the phosphonium salt seen here. The phosphonium salt obtained upon extractive isolation was dissolved in tetrahydrofuran, and after cooling to 278 degrees Celsius, the resulting solution was treated with N-butyllithium and paraformaldehyde, which then creates the alpha-vinyl triethylsilyl enol ether 17 in a 75% yield. The methodology for triflation was developed by other researchers and was used to transform the triethylsilyl enol ether 17 into the enol triflate derivative 9, seen here, in a 92% yield. This product, which is a colorless oil, was stored frozen as a solution in benzene for 2 days. Coupling of the enol triflate 9 with the benzylic reagent 8, seen here, in the presence of tris-dipalladium and the ligand 2-dicyclohexylphospheno 2'6' dimethoxybiphenyl in N-methylpyrrolidone at 70 degrees Celsius for 20 hours creates the metathesis substrate 7, seen here. Warming of a 0.2 molar solution of this product with a second generation Grubbs catalyst in dichloromethane at 45 degrees Celsius for 5 hours leads to a highly efficient ring-closing metathesis, forming the tetracyclic diene 18, seen here. Direct addition of dimethyl dioxirane in acetone to the unpurified product solution at 0 degrees Celsius leads to stereoselective epoxidation of the tetrasubstituted alkene, which affords the acid-sensitive tetracyclic diene monoepoxide 19, seen here. Without purification, the epoxide 19 is hydrogenated in benzene under 500 psi hydrogen gas in the presence of a Wilkinson's catalyst and solid sodium bicarbonate. The saturated product, epoxide 20, undergoes selective eliminative opening with lithium diethylamide in tetrahydrofuran at 215 degrees Celsius, which creates the conjugated allylic alcohol 21, seen here. Cleavage of the triisopropyl cycloprotected group with tetra-N-butyl ammonium fluoride in tetrahydrofuran and oxidative cyclization of the resulting phenol with benzene in a mixture of dichloromethane and hexafluoroisopropanol provides the cyclohexadienone 6, seen here in a 50% yield. The synthesis of the key azeto-alcohol intermediate 5 is achieved in 3 steps from the cyclohexadienone 6. This completes the synthesis of azeto-alcohol 5, which is used to synthesize precursors to cortistatins A, J, K, and L. Now we will discuss the synthesis of the cortistatin A precursor. The synthetic route to the precursor to cortistatin A is initiated by protection of the 2-hydroxyl substituent of azeto-alcohol 5 with excess chloroacetylchlorine and pyridine. Cleavage of the tert-butyl dimethylsilyl ether within the resulting product occurs upon exposure to hydrofluoric acid, creating the alcohol 23 and 80% yield. Oxidation of alcohol 23 with des-Martin periodinane and dichloromethane at 0 degrees Celsius, followed by addition of methanol and solid potassium carbonate, gives the keto alcohol 24. Addition of N-bromosuccinimide at 23 degrees Celsius leads to stereoselective 1,4-bromoetherification of the conjugated diene, forming the bromide 25, which is directly subjected to nucleophilic displacement with potassium superoxide. After extractive isolation, the trans-diol methyl ether 26 is obtained in diastereomerically pure form. When combined with scandium triflate and trifluoroacetic acid in dioxane, the substance undergoes efficient 1,2 elimination of methanol, affording the azetodiol 27. Reductive dimethylation of the azeto group and diol protection with chlorotriethylsilane then furnishes the protected 17-keto cortistatin A precursor. This concludes the synthesis of the cortistatin precursor. Now we will discuss the synthesis of cortistatin A. Lithiation of 7-iodoisoquinoline with an equal amount of N-butyllithium in tetrahydrofuran, followed by addition of tetramethylethylene signaled by TMEDA, creates the corresponding 1,2 addition product in a 52 to 62% yield. Each tertiary alcohol intermediate is transformed into a trifluoroacetate ester with trifluoroacetic anhydride and pyridine N,N dimethylaminopyridine. When heated with tri-N-butyltin hydride and azo-bis-iso-butyronitrol in benzene in a sealed tube at 100 degrees Celsius for 1 to 2 hours, each trifluoroacetate ester undergoes deoxygenation to provide the final 17S configured reduction product. This concludes the synthesis of the final product, cortistatin A.
So what is the significance of this new synthesis of cortistatin A? This new synthesis allows for production in much greater yields than what can be acquired from natural sources and has little to no deleterious effects. This is due to the 3D nature of the molecule. Of over 400 tested kinases, only 2 are affected by cortistatin A. This was once thought to be unachievable. This means that it is an effective treatment against hard-to-treat cancers like AML. HIV is still a major problem in the United States. Although many drugs have the ability to save a patient's life, the dormant virus is very difficult and expensive to keep at bay. Cortistatin A has shown the ability to put the HIV virus into a near-permanent dormant state in model organisms, which may eliminate the high cost of treating HIV in the future. Cortistatin A has set the example for future drugs regarding precision. Now, Either simpler alternative syntheses for cortistatin A with higher percent yield must be established, or simple molecules with the same effects must be discovered.